Hello dear student, I am Islam. Welcome to the fourth lecture of real analysis. Okay, so today we solve some question of NBHM PhD of chapter countability. Okay, and this question are very useful for CSIR NET Aspirant. Okay, when I was preparing for CSIR NET Aspirant, I solved NBHM PhD question, and I know NBHM PhD question are equivalent to part C question of CSIR NET. Okay, and this is very important question. If you solve NBHM PhD question, then you have almost done preparation of CSIR NET part C. Okay, so today we will done almost 5 or 6 question of NBHM PhD. Okay, and this MSQ type question, and there one question left in this tomorrow video, in a study video, and so we will solve that question. Okay, and after that I will, in the next video I will solve the remaining question of countability, and I close the chapter countability and I go to the second chapter sequence, I think. Okay, so let's start. Okay, so this is the first question, and I think this question came in NBHM PhD. See, this question, was asked in NBHM PhD. This NBHM PhD 2006. Okay, so this MSQ type question is type is MSQ type, or you can say it is net equivalent net part C type question. Okay, so see, and our chapter is going to be countability. Okay, countability and countability. Pick the countable set from the asking the pick the countable set from the following. How many set are countable? Okay, so all those is a set. See, option A. Option says that I'm naming it S. Okay, it says that alpha belongs to R such that alpha is a root of polynomial. Alpha is a root of polynomial with integer coefficient. Means you can say P alpha equal to 0, while Px is nothing but a polynomial with integer coefficient. You can say Ps belongs to Zx. Means P is a polynomial and its coefficient are coming from integer. Okay. Okay, this set. So all know the you can say the roots of polynomial. You count the you have to accompany, or you could say collect the roots of polynomial with integer coefficient. Okay, so this is the nothing but the set of algebraic number. You can say set of all algebraic number. Okay, we all know set of algebraic number are countable. Okay, set of algebraic number is countable, so you can say S is countable. Okay, so option 1 is correct. This countable set. The complement of the set are, okay, in above means it is complement. So you have to know a result. Okay, this is result I'm picturing this. Okay, you can say whole complex plane. It is a whole. If you think it a whole complex plane, then this set of algebraic number and set of transitional number. Okay, if A is a set of algebraic number, and I'm assuming that a set of algebraic number is set of all algebraic numbers. Okay, A, and T be the set of all transcendental number, transcendental number, set of all transcendental number. So if you make A union T, then it gives whole C. Okay, full complex plane. Okay, so A union C gives whole C. Set of algebraic number is transcendental number. So obviously A complement, you can say the complement of the set of algebraic number will be set of all transcendental number. Okay, because they are disjoint. So complement set of algebraic number is transcendental number. So complement of R is transcendental number. Now transcendental number set is not countable. Okay, this transcendental number set is uncountable, because if we know A, suppose A is we all know set of algebraic number A is countable. Okay, CTBL. Now if T is also countable, means set of transcendental number, if it also countable CTBL, okay, then it will imply A you count union of two set. This is countable, this is countable. So union of two countable set is countable now. But C then this gives C is countable. Okay, C is countable. But we all know C is uncountable now. We all know set C is uncountable. This is an uncountable set. Okay, so this set never be countable. Okay, this is uncountable set. So complement of the set algebraic numbers is transcendental number. A transcendental number is uncountable. Okay, so it is not correct. Option 2 is incorrect. Now going to option So correct option will be A, but option B is incorrect. Now set of all points in the plane, in the set of all points in the plane with coordinate rational. Okay, set of all point plane. Since to identify points in a plane, okay, you have to think in 3 dimension. Means you need a point whose coordinate are x, something like x, y, z. Okay, it's saying that a set of all points in a set of all point, you can say this is the set. Even the option C, this set of all point x, y, z in the plane. Plane means it's subset of R cube. So set of all point in a plane such that which coordinate rational, means x, y, z are rational. X, y, z are coming from, you can say, rational. Set of all points in a plane which coordinate rational. Okay, so you can say S is nothing but is equivalent to this set. Okay, but this is nothing but q cross q. Okay, this coordinate coming from q, this coordinate from q, this coordinate from q, set of rational number, the q cross q. Now q is countable. We all know q is countable. The series finite product of q, 3 product q. So it is we all know finite product of countable set is countable. Okay, so this is countable. This is countable, so S is countable. So set of all point in a plane is countable. Okay, so option C is answer. Okay, now any subset of R which is label as 0, any subset of R which is label as 0 is countable or not? This is not countable. There is an example. You can think that if you choose the example K, or you can write C. C means not C, English letter C. It is Cantor set. Okay, it is Cantor set. Hope you know this result. Cantor set. A Cantor set is a set which is uncountable, but it has label as 0. Okay, Cantor set. How can this found? Cantor set is nothing but you have to, there is a construction. If you assume there is a closure 0 on, first divide it 3 part, means 1/3 and 2/3. Okay, and take out this part. Take out this part, then you have to left with 2 part, na 0 1/3 and 1/3 1. Okay, name it K1. K1 it will be 0 1/3. Okay, and union 1/3 union 1. Okay, after this, do the same process with this. Do this the 3 part and left this part. Okay, then you get union of these 2 part. Okay, and do this 3 part and left in delete this part and make union with this part. So you K2 will be union of 4 part. Okay, this one first part, this one second part, this one third part, and this one will be union 4th part. Okay, if you understand, this 0 is first coordinate will be 0 on one end, and last will be, okay, the union of 4th interval, union of 2 interval. Similar, you will do similarly. Okay, and after that you will take the intersection. C is the intersection each Kn. Okay, and equal to 1 to 3. Okay, so this set C is called Cantor set. Okay, so this set Cantor set is, this is uncountable set. This is a result. Okay, there is proof also. This is uncountable set. Okay, and but this measure is 0. Okay, this set is measure 0 set. You can say level measure mu C is 0. Okay, so Cantor set is uncountable set which is level measure 0. So using example of Cantor set, this will be incorrect, because Cantor is a uncountable set which is measure 0. Is saying that any countable set is measure 0, but Cantor set is uncountable set which is measure 0. So D is incorrect. Okay, so A and C are correct option in the question. Hope you understand my solution. Now if you any doubt, you can always ask in the comment section. Okay, so okay, now come to the next question. Okay. This question is from NBHM PHD 2011. Okay, define if the following set are countable or uncountable. Which of the following set countable or uncountable? Okay, collection of all finite subset of n. Okay, this was done in previous video. Collection of all finite subset of n. Okay, you can say S, let S be the this set. Okay, assuming S be the this set, means this is the collection of S be the collection. I mean X be the collection. Is the collection of all finite subset of n. Okay, is the collection of finite subset of n. Then we can say from here that S is equivalent to the set this n cross some finite times. Okay, because finite subset of n are like the form na collection of finite subset of n. You can say S be with the set with this member, either 1, either 1 2, either 1 2 3. This will be, this set will be in S. Okay, so you can say, you can see here easily that S is isomorphic, or S is equivalent to the set n cross n cross n. Okay, now this is if you take its cardinality, the cardinality of S will be nothing but cardinality of, become this n cross n cross n cross na. So this will become cardinality of n cross n means cardinality of n, and cardinality of n natural number cardinality, and natural number cardinality alpha naught, and this is alpha naught, and this is also alpha naught. So alpha naught power, you can say it is n times, n times 5 times na. So alpha naught power n, so this is also alpha naught countable. So this set is cardinality alpha naught means this set is countable na. So this is countable. So collection of finds also n, this is countable set. Okay, you can say this is countable. Now collection of infinite sequence of positive integer. Okay, B, what saying it? B, we say collection of infinite sequence of positive integer means if you name it the set S2, then it is collection of infinite sequence. Infinite sequence means if the collection of F, those mapping from sequence means n mapping from infinite sequence of positive integers. Okay, means Z plus. So you can say those F belongs to this set, so the F is a mapping from n to Z plus. Okay, because it is collection of infinite sequence. We all know every sequence is a mapping from natural number to a set. It says set of positive integers. So if to codomain, take codomain Z plus. Okay, so it is collection of all sequence of positive integers. Now what is if you find the cardinality of this set, so cardinality of S2 will be nothing but cardinality of the, you can say this is A, this is B. Okay, so you can say cardinality of B means Z plus to the cardinality of A means natural alpha naught. Now Z plus is cardinality alpha naught, and natural cardinality alpha naught, and we all know this is alpha naught for alpha naught will be 2 to alpha naught. Okay, 2 to alpha naught is nothing but continuum, means uncountable. Okay, I have done this by this result, alpha to beta so equal to, if alpha beta cardinality, then alpha 2 to beta, if alpha less equal to beta, this is the result. Okay, then 2 alpha C, so is key, so C is uncountable, so this set B is uncountable. Okay, so this set B is uncountable. Okay, not countable. Now collection of all roots of polynomial with variable integer coefficient, it done previous question. Okay, it is countable na, set of element number. Okay, we all know set of element number is countable, so this goes countable. So collection of finds of n is countable, collection of infinite sequence of positive is uncountable, this uncountable, this set. Okay, and collection of all roots of polynomial means set of element number, the set of element number is countable. Okay, so first one countable, second one uncountable, and this is countable. Okay, now we are moving to another question. Okay, this is quite similar. This question came in NBHM PHD, 2012. Okay, NBHM PHD 2012 question. Okay, so which of the following set are countable? It's saying the which of the following set are countable. So first we are looking from one by one. Okay, so see, set of all sequences of non-negative integers. You all know every sequence is a mapping. So you can see, if you take F from the set, so F is a mapping from natural number to non-negative integer, means Z plus union 0. Okay, so F is a mapping from Z plus union 0. This set. You have to determine the cardinality of this set. This set is equivalent, is nothing but this set. So S set is a set of sequence, so it is mapping from natural number to Z plus union 0. But this set is cardinality alpha naught, you all know. This set is also cardinality alpha naught, you all know. Okay, so what is the cardinality of this set? S will be cardinality of alpha naught power alpha naught is done, alpha naught means 2 alpha naught. Okay, 2 alpha naught is C continuum, so it is said uncountable. So this set is not countable, so incorrect. Now set of all sequence of non-negative integers with only 5 number non-zero. Okay, see B is saying that set of all sequences, those F such that a sequence of non-negative integers maybe is sequence means, so it will be natural number, so and it's a sequence of non-negative integers, you can say Z plus union 0, but there is a restriction with final number term is non-zero, means you can say xi is non-zero for all I equal to you can say f of xi. Okay, because image are sequence na, f of xi, those name it S3. So f of xi is non-zero for I equal to, you can say n up to n, and remaining are 0. Okay, and f of xi will be 0 for all, you can say otherwise. Okay, means it is, if it's a non-zero for only 1 to so on n. Now other are not other 0. So you can see this if this f is only to 3 n image na, fx1 fx2 fx2 so on fxn. Okay, and this is nothing but non-integer this is non-integer, and remaining member are 0 is set. Okay, so this set become countable na, only this member are left, so it's countable na, this set, so no doubt is countable. Okay, so settable sequence of non-integers is countable, okay. Set of all roots of monic polynomial. Monic means leading coefficient 1. The polynomial which have leading highest degree coefficient each one is monic polynomial with one very less null coefficient. Okay, this is also set of eleven number. Subset of set of you can say this set. If you name it this set S1, then this is the subset of set of eleven number. Okay. Now, set of eleven number is countable. This set is countable, na? Set of eleven number is countable. So subset of any countable set is countable. Okay. So this is also countable. So in this question, correct option is B and C. Now, go to the next question. This question asked in NBHM PHD 2013. NBHM PHD 2013. Okay. It's saying A is the set of all sequence of real number. Okay, means A is nothing but like this. A belongs to this set. So if is sequence is making from natural number to sequence of real number, so codomain will be obviously R. Okay, so what will be cardinality? You can easily find cardinality. Is B is A is B. So cardinality will be total function will be cardinality A to cardinality natural number. So cardinality is continuum and cardinality is alpha naught. Now C power alpha naught is you obviously C na. C power alpha naught is obviously C. So now A B is a set of all sequence of positive real number. So you can say B is this. Mapping from sequence, so sequence mapping from natural number to is saying the positive real number, so its codomain will be R plus. Okay, now find the cardinality. This is the cardinality of B. Cardinality will be cardinality of R plus in cardinality of natural number. Cardinality R plus will be continuum, and cardinality R not C bar will be again C. So it is also continuum, means uncountable. So A is uncountable, B is uncountable. Okay, now C is the C01. Okay. Class of real root function on G1. C01 is also uncountable. Okay, is also uncountable. Its cardinality is also C. You can say because this is capital letter C. Okay, it is capital letter C and this is continuum. You can say this is continuum, not C. Means uncountable. Okay, so C01 is uncountable because this set belongs to this set. Na C01 you can say this set. You can say this set S equal to 1x square so on infinite set x to n. This set is belongs to C na. This because all functions are continuous on C1. Okay, so this set one infinite member. Okay, so how it countable? Okay. So C1 is uncountable. Or D is R is also uncountable. Okay, you know this R is also uncountable. R is cardinality continuum. Set real number is continuum na. So the each of the following set is cardinality of C, means continuum. Okay, so all set have same cardinality. This A is correct. A and B have same cardinality. No, also remain 2 is also same cardinality. A and B, A B have same cardinality as C. So B is also correct. Now it says A B have same cardinality, but C is different from C. No, incorrect. So in this question, correct option will be A and B. Okay, hope you understand. If you any doubt, you can always ask in the comment section. Okay, so we are going to the next question. Okay. It is given here. See, set of 11 number definition given. Okay, I have told you previously there are two type number, 11 number, transition number, and there is complex number. Okay, and they are disjoint both set. So it says set of a real number is algebraic if it root of a non-zero polynomial, at least one integer coefficient. Okay, otherwise number is transcendental. So it says algebraic number are dense in R. Okay, algebraic number is a set of algebraic number and it is a transition number. Okay, it is complex number. Okay, so set of algebraic number is dense in C. You have to know this. Set of algebraic number is dense in C. Also, set of transition number is dense in C. You cannot separate this. Okay, dense in also C. Both set are dense in C. Okay, you have to remind this. No need to prove this. Okay, if you prove it, it will give take long time to prove. Okay, so I am not proving it now. And set of algebraic number in dense in C, set of transition number also dense in C. Okay, so both are correct one. Now option 30. Suppose these are algebraic number. Okay, So if you can check it, okay, cos pi, you know that cos pi x and cos sin pi x both are algebraic, okay. You can say when x is rational number, when x is a rational number, then this number and this term are algebraic, okay, algebraic. So here x equal to pi, if it is x equal to 1/3, it is a rational number, 1/3 is a rational number, 1/3 is a rational number, so it gives cos pi by 13. So this is obviously algebra number, okay, this is obviously algebra number. So option C is correct also. So in this question, option A, B, C are also correct, okay. So all options are correct, A, B, C. Now going to the next question. This question also quite similar, okay. This question asked in NBHM PhD 2016, NBHM PhD 2016, okay. This is also MSQ type question. Which of the following set are countable? It's saying which of the following set are countable. So see, set of algebra number, we all know it is countable. I told you set of algebra countable. So option is correct. Set of still increasing sequence, infinite sequence of positive integers. It means this says that if to construct a set S, the set of sequence, it means it is mapping from natural number to positive integers. Infinite sequence of still increasing sequence, infinite sequence of positive integer, and such that this whole fn plus 1 still increasing. It's saying still increasing, na? So fn plus 1 will be greater than fn for all n, okay, this set. So if you still increasing sequence, so if this set will terminate in nothing but if you not consider this restriction, okay, so this current will be then, if not consider restriction n plus still increasing, then this gives z if not and countable natural number, if not, so this is continuum, okay, this is uncountable. But you have to remind that there is also restriction, maybe fn plus 1 greater than fn also, okay, fn plus 1 greater than fn also. Now fn plus 1 greater than fn also. So one more restriction, that fn is still sequence will be still increasing, okay, fn plus 1 greater than fn n equals to n. So this condition does not violate this, okay, this continuity. If you because you can create infinitely many sequence of, you can create infinitely sequence of positive integer which is still increasing, okay. How? See, you infinitely get, try to look at this sequence 1 2 3 4 5 6 7, okay, starting from this sequence, okay, x1, and try, is saying positive integer, na, it's saying positive integers, okay, coordinates should be positive integers, so image will be positive integers. If you choose this sequence x1, and there are another sequence start from 2 3 4 5 6 7 8 so on, okay, and try another sequence s3 starting from 3 4 5 6 7 so on, and next start another sequence from 4, next 6 7. You can, so you can go for so like this, okay. If you go for like this, you can uncountably many sequence, uncountably many sequence, okay, of still sequence of positive integers, okay. So this set is also uncountable, so the B is incorrect. Now set about infinite sequence of integer which is arithmetic progression, this is countable, okay, because it's saying set of all infinite sequence of positive integer which is arithmetic progression, means suppose this set contains the term like this a, if it a then it a plus d, then it a plus d, means there is a common difference, okay, and nth term will be a plus n minus 1 d, okay. See, you can count this term, okay, first name it x1, then x2, then x3, then xn, okay. So you count, na, x1 is 1, x2 is 2, xn 1 plus 2d, x3 is 1 plus x0, x1, x2, and it is xn minus 1, okay. So xn will be a plus nd, similar like this, okay. So you can count this term, because there is n, so in case h0, then a plus a1 is a plus nd. Using this you can count this number, a plus 2d, and xn is a plus n1d, is in this n, so you can count this number, okay. So this is countable, so option A and B are correct answer. So in this question option A and B are correct answer you can say. Okay, so option B, not option C. Option C. So option A and option C are correct answer. Okay, B is incorrect. Now, so we have solved, I think, 5 questions of NBHM PhD. Okay, this question is very important question in PhD. This is the first question, this is second question, this is third question, this is fourth, and this was 5 question in NBHM PhD. Okay, we have solved also this 6 question of NBHM PhD. Now we are going to solve a CSIR NET question. Okay, this question left in the previous video, so I have taken that question. Okay, so this is our last question, and in the next in the tomorrow video we will discuss the remaining question on remaining question control. Okay, and after it we close this chapter, and so we can go to the next chapter. So please see this. X denote the 2.01. Okay, write xj equal to means each xj is cardinality 2 for all j. Okay, and let y equal to infinite product of xj. You can say x1, x2, so on. Okay, so from here you can say the cardinality of y will be cardinality of x1 cross cardinality of x2, cardinality of so on. So it's cardinality 2. So cardinality 2. How many times? It is alif node times, so it gives 2 per alif node. Now 2 per alif node is quantum, so y is cardinality quantum, means y is uncountable, na? So y is uncountable. Okay, so y is not countable, this is incorrect. Y is uncountable. Now this C, cardinality of y will be is uncountable quantum. Okay, cardinality C is also quantum, so this is C equal, na? So this is equal. Now is finite product x1 expression, so finite product of countable is countable, so this is countable, but there is also countable union. So this is countable and there is countable union. So countable union countable is countable, so it is countable, but it is saying uncountable, so it is incorrect. Okay, so hope you understand. So this question is correct option is option 2 and 4. Okay, so I have also solved all questions. Okay, so please subscribe my channel and follow my channel. If you have any doubt, you can always ask in the comment section. Okay, and we will keep more solutions in upcoming videos. Okay, and also lecture videos. Don't worry, please follow my channel regularly. You will get all things here. Okay, so thank you, and please subscribe my channel. Thank you.